Chenpei, I think you can start.
Okay, so let's get started. Hello, everyone. Welcome to today's group meeting. Today, I'm going to present a Sensys paper titled OneFi, One-Shot Recognition for Unseen Gesture via the COTS Wi-Fi. So here is today's outline. I will first introduce I will give a brief introduction to this paper. And then I will show you the system design in three perspectives: the data collection, virtual gesture generation, and few-shot recognition. After that, I will talk about the evaluation in this paper and finally conclude. So nowadays, we have more and more human-centered applications thanks to the development of machine learning. Now, machine can understand and accept flexible user input. One of these enablers is called human gesture recognition. The recognized human gesture can be used for the virtual reality, medical control, and the smart home applications. The goal of the HGR is actually quite simple. It is to understand the human gesture given some physical signals. Traditionally, we may need the camera to capture the image or the videos that contains the human gesture, or we can use some wearable device to record the motion information. However, these two methods are far from satisfactory. Image video leaks personal information, and using the sensors may bring some inconvenience. So as a result, the Wi-Fi sensing becomes a promising solution, which is convenient, private, and ubiquitous. But it is not a brand new story to adopt Wi-Fi for a Wi-Fi signal to gesture recognition. So in many previous work, the workflow to define the workflow of the Wi-Fi based HDR is to define the base gestures. They collect the data and train the model. In fact, we do not have much predefined gestures classes, and we also don't have much data. So here comes a straightforward problem. So how about the unseen gestures which are not included in the base gestures? So that can be a serious problem. Let's first discuss why the unseen gestures are important. Because it links closely with the application. One more gestures are actually needed for user to precisely interact with the computer. And also, the system must have some capability for a user to use his own gestures. Okay, so what could we do to make it possible? Usually, we follow supervised methods. That means we collect the data first, and then we train it, we want to train it effectively. So we need to have sufficient supervised information. The system may ask the user to do a personalized gesture for 20 times, but you can say this is totally undesired because they need quite a large user effort. So what makes it worse, we have another overhead called the retraining overhead. Even with the collected data, the whole network needs to be retrained to include the new gesture classes. So we all know such process is time and computational costly. So to be brief, current methods limits the system's scalability. Before digging into their design, let me give you the problem definition. So this system is expected to recognize a few base gestures. That is that is for all human Wi-Fi based human gesture recognition tasks. But beyond that, we also expect this system when when introducing some unseen gestures, the user may only need to collect one signal sample for any unseen gestures. And we also want the model to faster adapt to new data without retraining the whole model. So that is the ultimate goal for this design. Let's move to the system design. This is the overview of this system. So in order to develop a system to learn the unseen gestures using only a few shots or even one shot, we still need a base class data set with sufficient gesture data examples. So they first collect the collect the base data for training. They have the base class data collection, pre-processing. And here is their first contribution called virtual gesture generalization. So it is actually a data augmentation method specifically for the Wi-Fi gesture recognition. The process is shown in this blue dash rectangles. Actually, it uses the data from these base classes. They do some nonlinear optimization. Actually, it's for inverse problem. They use the velocity to Doppler mappings and using this given data to generate some virtual data that can augment the base classes. So they claim in their paper that such process can increase the data and boost the training accuracy. And then they have also collect the one-shot the one-shot data set. This one-shot data set is actually the unseen data set. All these entries are unseen human gestures. They also follows the data collection, pre-processing, but this data set size is much smaller than the base data set. So after this pro-processing, the model is then trained based on these two data sets. It is actually trained a feature extractor on the large base data set and then fine-tuned on the one-shot data set. So in this way, the system can learn the representation of the unseen gestures without retraining. So it can alleviate both the data collection overhead and training overhead. So here are the four main steps in this system. Prepare the training data, augment the data, they prepare the unseen one-shot data, and for the model training and one-shot fine-tuning. Specifically, the augmented training data in this red rectangle, they enrich the prior knowledge. So the model training and they enrich the prior knowledge, so the model training can be more effective. And for the model training, one-shot learning framework, and they're using the self-attention-based backbone, this too is targeted at alleviating the training overhead. So in the next few pages, I will show them one by one. Okay, here is the data collection. Why this Wi-Fi signal can bear the human gestures. So here is the reason. So we consider a transmitter, and consider a transmitter is a commercial off-the-shelf Wi-Fi devices. It can generate and send the packet to a receiver. So when the radio signal is propagating in the environment, it will reflected by the surroundings like humans or some other static object. So the channel state information is actually the attenuation, which is A in this equation, and the phase changes. The phase is that on top of the E. So this attenuation and phase are changed by the propagating environment. So if there is a human here waving his hands, the CSI also changes over the time. We also know that the EM wave interact with a moving object will cause a Doppler effect. So the Doppler effect is defined in this equation. So this dt here is the distance from the of the propagation is the propagation distance. So we can rewrite this equation called into this summation. One is the static path. It is all the background, some non-moving objects, and there is another component is due to the human gesture. It is dynamic and changing over time. So the goal here is to extract these components from the Wi-Fi signal or from the CSI. So by extracting this, it can then be it has some insufficient human gesture information. And here is the workflow for the data pre-processing. You can extract the data, the raw CSI step by step, and then and at last keep the useful part. So they first collect the raw CSI. They're showing two different subcarriers, for example. So the red and blue curves in this subfigure are representing different subcarriers of the Wi-Fi signal. The first step is to remove the DC offset, and because we know the DC offset is usually it's not changing over the time, so it is not irrelevant. It's not relevant to the human gesture, so we need to remove it, and then we also multiply this signal with the reference signal. Or called pilot signal. It is to remove the unwanted interference from the devices, such as the carrier frequency offsets or some sampling frequency offsets. So by using the known reference signal, it can be effectively removed from the observed CSI signal. Afterwards, they apply a low and high pass filter. So it only keeps using some prior knowledge. So we only keep the frequency of interest and remove all some other noises. And at last, they use some PCA analysis. So in this way, it can do the dimension reduction. It also removes some unwanted noise from the useful signal. At last, it just process this time domain signal using the short Fourier transform. So we can at last derive the Doppler spectrum showing in this 2D figure. The blue means the value is small, and the red color means the value is large. So it is it has two dimensions, and the x-axis represent the time, and the y-axis represent frequency. Let's look at their first contribution called the virtual generation. So the goal of this step is actually to use the signal model to generate the data from the existing examples. So let's take an example to convert a real ground truth push forward to a virtual push left. So we know that these two different human gestures have some similarities, but how we can change it completely to another gesture we have never seen before. First, they collect the push forward data because it's real data, so they already have the Doppler spectrum, just like I mentioned, the pre-processing and all the signal processing process, they have the Doppler spectrum, and they are solving a nonlinear inverse problem to map the Doppler spectrum to the velocity distribution. If you remember, I should put an equation here. So actually, this one is the represent the velocity, and this one represents the Doppler effect. But it is not a linear mapping, so we may have lots of velocity. We have a velocity distribution, and they all point to the same Doppler component. But fortunately, we have many examples in time domain, and maybe we also have more than one receiver or antennas. So we have sufficient samples to formulate a linear or to formulate an inverse problem. So we can solve that inverse problem to actually transfer from the Doppler spectrum back to the velocity distribution. So we now know that the signal model of a velocity distribution. So we manually add additional 90° to this signal model, and we recalculate this Doppler spectrum as a forward problem. So at last we can derive a new Doppler spectrum. This new Doppler spectrum is actually means some people is pushing his arms to the left. So the transform result is showing these two figures. This subfigure A is actually a virtual gesture transformed from the pushing forward to the pushing left, and as a comparison, the subfigure B is real data. We can see these two figures is not completely the same, but they do have some similar patterns. And as a result, in this paper, they also increase the training set by 12 times. And they show it later that such data augmentation does increase the total accuracy. So that is all for the virtual gesture generalization. And they also use
Chenpei, I'm sorry.
Okay.
So obviously I'm not expert in this area, okay. But I'm curious, did they verify the push left? You know, you can really push left in real world, right? So you can get this kind of distribution. Or you also can, you know, use their approach to convert push forward to do the data augmentation to get the push left data, right? Did they verify those, the measured data with their augmented data?
Actually, this page actually shows the virtual gesture and real. They all push left. Sorry to
they all push.
This
okay.
is the comparison from the true data.
Okay. I didn't notice the caption. I thought the figure B is like push forward. Figure B is also push left, right?
Yeah, it's also push left. So the rationale or the reasons behind this kind of virtual gesture generation is actually, you think of it when you're pushing your arm forward or pushing your arm to the left, the velocity of all the components of your arm are actually very similar. The only difference is just they apply additional degree, 90 degrees. So if you can model them, you can have a signal model. You just manually add this 90-degree, and you can calculate them without collecting the true data. So that's what they're showing.
So Chenpei, this is like the y-axis, so it's the frequency change, right?
Yeah, it's the frequencies on the y-axis.
It's a frequency, but if like one push left and another is push right, so that will have the the velocity, the direction are different. So the frequency change will also on different direction. So in this case, so one should be should be in the positive frequency, another should be negative frequency. But from this figure, it seems all of them so are on this at this frequency 0 hertz, but I cannot see this this inversion.
Yeah, of course.
You know,
yeah. Yeah. Okay, go ahead.
Yeah, I think ideally, I think so. Like if you push left, so we can see that it has the positive direction. So all the frequency it should be above 0 hertz, and then the push right it will be the negative, like below the 0 hertz. But here I cannot see this phenomenon. If no, why can we like judge them as the push left and push right?
I believe this difference is related to the orientation of your transmitter and receiver. So if your transmitter and receiver you're not just standing in the middle of the transmitter and receiver. For example, they have you're in front of the transmitter and the receiver is on another direction. So maybe you are reaching your arms. It creates some additional multi-passes, and this passes is actually longer than the because it's not more. It's the multi-pass environment is actually, for example, the indoor environment, the multi-pass is rich. So
yeah,
the mean pass may be the the mean pass may be on the one directional, but in reality, it has very complex reflections, so nobody knows that whether or not, unless you are in a very small zone and you can control, you have the very good line of sight and you just shadow them. Maybe you have a very reasonable or very clear showing on one direction. But yeah, I mean, that depends on the environment, I guess.
I agree with that, like in different environments, so the situation is different. But here, if these two figures are from the paper, right?
Yeah.
Yeah, if from the paper, I think at least they should like give some sense or like to let us understand like why the left figure is push left, the right figure is push right. They should at least like give some explanation. So otherwise, if they just said, okay, you can see after the generate this is push left, but how can we know whether it's true or not?
Yeah, that's a question. I mean, but at last, their effectiveness can be shown in the training accuracy, and right.
Okay.
Ultimately, it has a classification accuracy to verify all this effectiveness.
But if we, how to say, just based on this classification results, how to say, we never know how did they do the experiment. Okay. Yeah, yes, it's done matter. So I think at least I think that if they want, they should be able to show some figure to clearly to show the difference on the reverse direction. I think it's possible, but I don't know why they just use this two figure. I think this two figure cannot convey any useful information.
Yeah, maybe I should show the equations, but I only put these two figures here.
Okay. Thank you.
Oh, all right. Yeah, thank you. And let's move forward to the few shot recognition. So after enhancing, actually the data augmentation is to enhance prior information in training data set. So what should we do next to recognize something classes or with few data samples? So this problem is actually called the few shot recognition. Let's first clarify the basics terms in the few shot learning context. We call the sufficient large data set with the supervision the base training set. And we also call the newly explored classes with few labeled data, the few shot sport data set. And we also call the examples we want to label, we call it query data set. So to train the few shot network, the first stage is to train a feature extractor on the training data set, which is shown in the equation in this red rectangle. So this loss function is to minimize the losses. Actually, is cross entropy on the training data set. So the F, the symbol F is actually the feature extractor, and the W and B are the classifiers. So after training on this big data set, we then apply it to the, we freeze the parameters F. That means we freeze the feature extractor and fine tune the classifier using the support data set. In this fine tuning stages, F is fixed, and we only they use the average embeddings WJ this WJ, the average embeddings extracted from the query data set, from the support data set as new W. So at last, when we want to evaluate the samples from the query data set, they just use this new classifier and this fixed feature extractor and this new derived classifier to evaluate, to label the unseen data based on the sign similarity. This process is shown in this blue rectangle. And next, the critical part of the few-shot learning depends on the effectiveness, the feature extractor, how many information can be extracted by the feature extractor from the base data set. So a powerful backbone network is needed. So in this paper, they actually choose the transformer as their backbone model. The reason to adapt to this, to adopt the transformer in the Wi-Fi HDR recognition is because the Doppler spectrum is essentially sequence data, and the transformer has a self-attention mechanism to learn the context information, and in view of the training process, transformer can be deployed in parallel, so it can train faster and save the training time. So here is the overview of the proposed Wi-Fi transformer. So it's just a standard transformer structure. The model, they use the Doppler spectrum as the input. Then they add this position embeddings to retain the position information. They train it using the multi-head self-attention blocks in this equation. So in the Q, K, and V here, they are all linear projections from the input frames. And at last, the model output is actually they choose the first output of the transformer encoder, because this model encoder and this model output can have the representation of this whole sequence. So that is the workflow of this Wi-Fi transformer. And in the next section, I will introduce their evaluations. So their experiment setup is shown in this figure. They employ a number of transmitters and receivers. The CSI is hereby extracted by using the COTS Wi-Fi devices, and they are also using open source CSI tool running on the Linux system. And the data they're using is they collect the data when the volunteer is standing in these 2x2 sensing areas. And in total, they collect 2,900 samples in 40 classes. Besides, they also collect 6 unseen classes to evaluate a few shot training. And at last, their performance metric is the classification accuracy. So first, they evaluated the overall accuracy. The OneFi, that is the system they are proposing, we can see in this figure that the OneFi outperform the current methods, the MetaSense and RFNet in all the few shot settings. The reasons behind may come from many aspects. They can be from their framework, their backbones, and the data augmentation they're using, and even the different hardware settings. So that's why in the afterwards, they show the impact of those potential reasons individually. And they begin it to discuss the effect of the virtual gestures first. So talking about the virtual gestures, that is data augmentation, they compare it with two baselines. The first baseline is they do not use data augmentation at all. The second baseline is an AE method. It is just to simply add some noises on the collected data. So the result is showing in the bottom left figure. We can see the naive data, data augmentation, actually, it does not improve the training accuracy and training and testing accuracy. But in contrast, the virtual gesture showing in the blue line, it shows the superiority in all the all data settings. So we can conclude these feature extractors is inferred to learn more prior information with the help of their proposed data augmentation methods. And then they compared.
Chenpei, I have a quick question here.
Right.
So can we use the traditional data augmentation approach, or not this kind of naive one? For example, we use GAN or something to generate some, augmented data. Is there any particular reason, the classical data augmentation approach cannot work? We have to propose a new one.
Yeah, they do not mention using GAN, but I think using GAN actually increase the training overhead, right? This one is quite simple. It's just use some physical model and suddenly it's done, and it has good reason, got good accuracy. But true, there did exist some other data augmentations, but it's not considered here. What they consider is adding noise, and they also discuss that the conventional methods for the cropping, padding, and rotation is not here. But it can be used in the Wi-Fi Doppler spectrum. So it's not reasonable to use some image augmentation methods, but you're right, you can use GAN, but they do not consider.
It was like, for example, in security, right? GAN is like a brute force approach, right? So it doesn't matter as long as you give me some kind of few figures or a lot of figures. I can use GAN to augment a new one, right? With similar features or something. This one is like, delicate, carefully designed approach, right? So like you mentioned, we use some physical phenomena, the change of that, I can do some inverse engineering to design this approach. But you can only argue there is pros and cons, but you cannot say, I don't care about this approach, Because again, everybody can think of that. Is that because we have very limited data? But I think for the gesture one, a lot of people work on that. It should be a lot of data, right?
Right. That's possible, because for the data augmentation, they actually do not care the unseen gestures. They're they're just to increase the labeled data in the base data set. That's true, actually. I agree with you, Dr. Pan. Yeah,
okay.
but the contribution behind is is their physical signal model. So that's why they want to compare it to this two baseline. It's not completely from the data, it's from the real world physical system.
Yeah, I agree. You know, just like I said, the GAN is like brute force, right? This one is like some calibrated designs, careful designs, you know, specific to this one.
Right.
But still, you need to compare something, right? For example, like you said, if you say GAN overhead is very high, I can accept that. But you cannot say, you know, I just put a very, very stupid, very, very naive data augmentation approach by just adding noise, and we compare the performance. It seems a little bit unfair. In particular, in nowadays, the learning is so popular and so widely spread, right? So
I mean, maybe they're just to show their method, their data augmentation methods can make some impact on the overall training accuracy. They're not comparing with something. Maybe.
But okay. Anyway, yeah. I think if we use a GAN to generate some, say, whatever we call it, virtual gesture, or just call augmented data, whatever, I think they have probably they have the same impacts.
Yeah, it can be.
I'm not sure, but you know, okay. Thank you.
Okay, so in their next evaluation, they discuss the effect of the proposed backbone, and they compare their proposed transformer with the LSTM and the LSTM plus CN structure. So they are all popular structures in this area. They prepare, they show their performance on these bottom left figures. And you can see the classification accuracy in this figure. The transformer models actually outperform in all few shot settings. And and you can see the LSTM one is the second best method. In addition, the also mentioned the CNN plus the LSTM structure, it can hardly converge. So comparing to the transformer, because the transformer can comparing to the transformer and the LSTM, this kind of structure using two different deep learning models. So in their paper, it just mentioned the training time, and actually the transformer do the best, not only on the accuracy, but they save the training time as well. And at last, the impact of the on-scene gestures. We know even for the few shot learnings, the more on-scene data will make this problem harder. So in order to show the effectiveness of their proposed few shot learning framework, they vary the number of on-scene classes from 6 to 20. Also, their results with different number of shots are also provided. We can observe from this figure, and it is actually as expected. Of course, the performance is decreasing as the on-scene classes increase, but the author mentioned, pointed out by adding some more gestures from 1 shot to 3 shots, the performance can achieve over 70%, even with a huge number of on-scene classes, say 20. So if you have more shots, the data, the classification accuracy can goes up. So they can say their proposed few shot learning framework is actually effective even when their unseen classes has a very large number.
Oh,
Oh,
sorry,
okay.
could you go to previous page? I wonder the accuracy here, do they include the classification result of the known classes plus the unseen classes, or is purely unseen classes?
They're only varying the unseen class. You mean the accuracy?
The accuracy, yeah. Are they talking about only for the unseen gestures, or say they're kind of for all the gestures, including the unseen one and the pretty known one?
Something I'm not quite.
Because like yeah, because there is a kind of probability, right? Because for example, I didn't remember exactly how many known classes you use, 400 or something, 200 or something.
40.
40, okay, whatever, right? So even you use 20 unseen, so probably the 40 is still taken, I don't know, more than 65%, right? So if that one as a base, right? So as long as you pick up the same known classes, definitely that should be accurate. And overall, the accuracy should be, if it's above 70, we can say, okay, probably there's some improvement. But if it's below 70, there's nothing improved, right? According to the probability, it's supposedly to
it can't be evaluated like this. For example, you say it does has, what you say is it does have some unseen data, but they also include the lots of known data. So that makes the evaluation unreasonable.
Yeah. I know. What I'm saying is just, just like I don't know, intuitive derivation, but it's not necessarily true. But what I'm saying is, I mean, more than 70 seems not that impressive, right? So even more than 60 is not impressive. Even more than 70 is not that impressive.
Yeah.
I'm not sure if it's only for unseen gesture. Definitely, it seems pretty good.
Yeah, that's true. I think it's quite impressive. They have very good.
Yeah, and also I think here this accuracy is just like this true positive. I think they should also measure false positive, just as Dr. Pan mentioned, like giving some unknowing, unknowing this gesture and let to make a classification. Probably he will make the wrong classification. I think he should also measure from another direction to show the performance. If it just show this accuracy, yeah, it cannot it cannot say anything. I think it cannot demonstrate it's good.
I get your point. You mean they set a very, for example, set a very low threshold, or maybe all cases just pass. Yeah, in that sense, yes, true. Maybe it's better to give another direction or using some equal error rate, the F1 score or something like that. It should be more reasonable, I think. But this one is just a classification accuracy.
Okay.
This is the final page of the evaluation. So let me conclude the other experiments in their paper. First, they also consider the impact of the number of receivers. They change the receivers from 1 to 4, and you can see when the number of receiver is 1, it's not that good, but if it's changed to 2, increased to 4, actually there is a very limited improvement. So the author claims the number of more receivers in the human gesture recognition is important. It's not that important in inferring the gestures, but it's still very important in the training process because you can collect more data for to train the model. And the rest of the evaluation, they also claims their model across can have the capability to cross environment, cross orientation, cross person, and cross location. So they really built a very robust system to for the human gesture recognition. So finally, let me conclude this paper. First, they propose a new system called OneFi. It is a one-shot HER system to recognize some unseen gestures using the COTS Wi-Fi system. And they propose a virtual gesture and the few-shot learning framework to mitigate the extra effort in the data collection and model training. And they evaluated it that such methods can achieve a higher recognition accuracy in various settings. And they say it is a very promising step towards a practical wireless human-computer interface. That's it. Any questions?
So I have one question. So for data support set and the base set, what's the difference?
The support set, the base set is a lot of data. It is a lot of data. They include some the labeled information. They're all known gestures, but the support data set is very few data samples, but also it is labeled, but their number of each class is limited. So it's actually to learn prior knowledge on a very big base data set, and they just transfer their knowledge in the support data set. So one is big, one is small, and one is known, one is unseen before.
Also, this like a one shot. This is unseen data.
Maybe I should show this page. Yeah, the one shot is the support data, and the another one is the query set. Query set is the samples to be tested. So they are trained on these two data set and tested on this data set.
Yeah, I know. So I know this step, but I cannot figure out. So why we need both this base training set and this support set? If we just do this base training set, I think it should be enough, right?
It's just to fine tune the classifier on this one shot data set, because it cannot be completely the new gestures actually needs some enrollment, or it's showing this few shot data set. It should be presented to the model, but it only has limited data samples. So that is a problem. We don't have enough data to actually effectively train to let the model distinguish the new upcoming gestures, but we can only give them one or two examples. They can suddenly know what is the newly defined gestures. So I think it's needed.
Yeah, but you mentioned that the best training set already have the label, right?
Yeah, they only have their known gestures.
Mm-hmm.
For example, you're using the VR system, you define a new gesture. Everybody don't know, you just create it called wave. So this example will never show in any existing data set. But you do not want to do it again and again to make this model, existing model, learn your new gesture. You just want to present it once, and this one you present it, it's inside the support set. So they just fine tune on the support set. Afterwards, the model will know your new created gesture, the wave.
Yeah, but it's strange. So I think for like they should like this just use basic training set and use this data augmentation to make it like to be sufficiently to like recognize and generate the all of the like this gesture. I think this should make sense. But here it add this few short set is looks strange to me.
Yeah, I agree with you, Dr. Ren. If you add the support samples here, what kind of benefit do you have? You cannot create a new label or new class, right? Because there's not enough data.
No, it's actually, it creates new classes.
But if it's create a new class, why don't put it to the base training set?
Because first of all, you need to retrain the model if you are creating the new data set, or the new classes. All the models need to be retrained on this new data set. And another question is, you don't have enough data. If you directly put your newly defined gestures to the original data set, it's imbalanced, and maybe the model cannot learn enough information from the very limited data set. Or you mean, so you can use the data augmentation? I got your point.
Yeah, I also got a point, but I don't think that is necessary. Even retrain, so what's the point? So what's the weakness? I think all these are done at the backhaul, at the cloud. So even if it retrains, it doesn't matter. And also when you deploy this system, so you can like already collect some data. You expect that they just use this collect data to do all the work. If later on you also need to like collect this support set to input, I cannot see. So what's the difference? Like why don't do it in the early stage? Or even like I put it to this base training set to retrain. I think it can solve the problem. So why is the need to have this additional component? I don't think it can save too much time. And also here, I don't think the time is a bigger concern, because all this we cannot expect the Wi-Fi device can run this model. All these are controlled by the either computer or the cloud. So they should be capable to do this training phase.
Yeah.
So do they I don't know. I kind of agree with Dr. Yuan, but if you think from their perspective, do they put more weight to the supported samples, or say, I don't know, probably they normalize the training data and also normalize the new sample supported samples? Whatever. What I mean is, do they put a new, higher weight to the supported samples, even those data, their number are very limited, but still they can affect the overall training model, learn model a lot. Have they done something like this?
No, what you are talking about is reasonable, but it's not in this scenario. All the models need to be updated from time to time. So maybe at last we'll have a big model that will include the new gestures into our base data set. But this is not the case we want to figure in this paper. This paper, they just focus on the scenario that we have a problem with our new gesture class is never presented in the base data set. We know that after a few months, maybe there are some updates and all the problem is done. But at this time, they want to cover it up. So they just borrow the few-shot learning framework. So even you have some unseen data, you can use very least overhead to make this system work. I don't mention.
I got your part.
Completely.
Yeah. Let me refine my question. Okay. So here, how can you fine-tune the classifier with a very limited support samples?
For this problem, this question, first of all, their feature extractor needs not to be updated on this small data set because they already trained and learns enough prior information on the base data set. So the feature extractor is fixed, is freezed in this stage, and they only need to compute the extracted features as embeddings and the use from the support data set, and they use this embeddings as the weights in the classifier. So they just discard the trained classifier from the training data set and use a new classifier we derived in the support data set. And with this classifier, when there is unseen gestures, it can recognize it as one of this class in the support data set. So that's their overall procedure. Just something very similar to the matrix to the embedding learning stuff. They just compare the cosine similarity you can see in this blue.
Yeah. I got your point. Okay.
But if they put this support set into the base training set to retrain the model, I think it can achieve much better performance, right?
Yes.
But I think what Chenpei try to argue is they don't want to waste the time to retrain the model. They use the already trained model, right? I do some small changes, do some add-on small training, I would say. I say small comparison, embedded training, learning. Then I can distinguish, probably this new suggestions, something like that.
Yeah. They just want to train it with least overhead, and at this time it can be used. Overall, the new data will be included in the base set, no problem, but it needs time.
But still, I mean, if it's I kind of want to echo Dr. Yuan. If it's not like real time, it's like, I don't know, it's like, offline things. Why don't you put the support data samples into the original training? Because periodically your computer or server, whatever, they need to update that trained model, right? So the continuous training, right? So why not? It only work on the scenario, say, I don't know, you have very limited computing capability, so that you cannot do the offline training. You can only do some small modification for that.
I don't think so. They just they just say the training and waiting time, the data collection, they are all overheads we need to avoid. So to avoid this, we adopt this framework.
And in practice, this support set, how to say, is not always available. if there's no this support set, how to make it work? Right. So it seems it's very hard to to figure out some real world scenario. Why it's so hard to guarantee that you always have this support set?
Actually, the support set, for example, the support set, one class only needs few shots or even one shot. So maybe you just do it once and enroll it in the system. Of course, comparing to the base set, the collecting overhead or the efforts in collecting a support data set is much smaller.
Yeah, so that's the problem. So you need to like collect this support set and also need to label it. I think it's how to say its overhead is even much higher than the retraining. Right, because this should be the like a human label to work on this.
But retraining also need to do that. But retraining also needs training time. I got a little bit. I don't know how to answer this.
But again, you know, if we don't care about the time, right? Because you do the gesture recognition, right? I mean, it's not like real-time thing. It's not like you wave your hand like a new gesture, and probably in 1 second you need to do it again, and you wanted the things to be classified or, you know, want to be known, recognized by the machine, right? It's like you wave your hand, new gesture for once, and probably will wait for another day, probably another month. If it's like support samples, like you said, it's really show up, right? Then you have enough time for the retraining.
Yeah. So yeah, that's my case. So compared to this like generative support set, I think this retraining time is how to say is negligible, right? Probably retrain. So assume that it's like 10 minutes, but you collect this support set and you label them. I think probably it's need 1 hour. So this retraining time is how to say it can be ignored.
I mean, to include a new gesture, even when you train a whole model, it still needs labeling work. It still needs collection. It doesn't save anything.
Yeah, it's needs that I mean that so in that case, so if I already like spend this like 1 hour or 2 hours to do this, why I cannot spend another half hour to other things to do the retraining, right?
But it's
But
not that complicated. For example, you just wave your hand. It doesn't take a few seconds.
Yeah, so yeah, so I think I don't know why they have this design. So I think the ideally so it's expect that I just use this base training set. That's enough. So we don't need to have this support set. So and also once the system is deployed, we don't need to make we don't need to make any change. This is expected.
So Chenpei, so in their evaluation, they don't compare the case Dr. Yuan mentioned, right? So if we combine the support set to the training set, you know, and retrain based on all this data, they don't compare with this case, right? I saw they compare with only user base and 1 shot and few shot something. I'm not sure if it's talking about this one.
But I need to say, in my opinion, it's a completely different research problem.
No, for compare, so there are 2 comparison, so 2 baseline that can be used for compare. One is that there's no support set, just use the training set. Another is that okay, I have this support set added to the training set to do the retraining. I think it's so the experiment should compare to these 2 cases to show that so why they need this 2 stage. and also show the importance of each stage.
Yeah, it's hard to answer that.
Anyway, so we don't know what they are thinking, so this we don't need to argue here. We just have,
I guess the fusion learning framework is a studied field. So in machine learning, there are many survey papers and other papers. It's just like everybody agrees that there's kind of learning problem called fusion learning, and they all follow this kind of fashion.
yeah, probably so. They just want to show they have different design with other work, so they have they add this part.
Yeah.